So the content of this presentation is about how we determine where to put a detector and why. And so the question is very provocative for a reason. Um, why is that detector there? It's amazing how many times I personally walk through facilities, and when I see a gas detector or a fire detector, I ask whoever's with me, who's pleasant enough to do the walk down, I ask them, why is that detector there? I'm always curious. And I am surprised how many times people look at me and go, I have no idea, Jim. No one's ever asked me that question. And it's a challenge. I know that I know there are some underwriters that wanted to be on this in this session, and they may or may not pop in. Everybody's being admitted automatically. I'm not going to keep track of that. And the reason they want in is because they ask the same questions, and they're trying to understand this too, because they want to understand when they tour a facility. The same thing's true with the regulators and stuff, right? So what they're trying to understand is whether or not you understand what's going on in your facility, and whether or not you've used good engineering and documentation to justify not only your process safety management stuff, but that you've actually verified you have a good idea why a detector's there. And you don't have to give them an exact answer. You can be as simple as, well, we hired a company to determine where they need to be, and that company told us to put it right there, and which way to point it, and what settings to set it on, and why. And if you want, we can go find that document and go through it. And that's actually a great answer. Most of this is going to be based on the International Society of Automation's technical report 80. I just call it 8407. It's on the guidance on the evaluation of fire, combustible gas, and toxic gas systems. We follow this deliberately and very carefully. It's probably one of the most advanced documents on fire and gas, performance-based fire and gas type stuff available on the planet. The ISA 84 committee is the committee that basically wrote what has become the IEC and the ISA's 61511 standard, 61511, which is the process safety standard. And in the United States, OSHA, our Occupational Safety Hazards, whatever, the thing that's designed to keep workers safe, has actually recommended following that standard as the way to meet your process safety management requirements that come out of the 1910 law, actually, in the United States. All right, so let's go ahead and see if I can get the slides to advance. This is always interesting because, like I said, I'm inside of a different operating system, and it's going to be difficult. This is who's speaking. I'm Jim McGlone. I am not a young man. I think I'm a young man, but I have been in the industry for quite a while. I'm a technical consultant for Conexus. I'm the chief marketing officer at Conexus too. We joke about this because I'm actually, I have a nuclear physics degree, and I used to run nuclear power plants for the United States Navy, and Conexus has to have a marketing guy who's an extreme technologist and really understands stuff, complicated things like control systems and physics. Otherwise, I would fail miserably at this job. I am the co-author of a book called A Security PHA Review for Consequence-Based Cybersecurity from the International Society of Automation. That book actually is a really useful book for evaluating all your safety functions to find out whether any of them are vulnerable to a cybersecurity risk. So I would encourage you to think about that if you're in the process safety business. I am a certified industrial cybersecurity professional. I have global certification from SANS. Just because I'm a controls guy. I've learned how to program just about every kind of controller and PLC and software program, HMI, historian, you name it, that was ever invented, and was very instrumental in the development of Rockwell Automation's Rockwell software product line. I have some degrees, and I am a fire and gas mapping instructor. I am not the instructor by any stretch of the imagination. The guy who actually teaches this class for the ISA and is the head of our software development is he owns or holds patents on a bunch of this type of stuff and is absolutely, I would consider to be probably one of the best in the world at understanding how to do fire and gas mapping. And so you can actually take an ISA course from him. It's the ISA E56P course. It's taught regularly, about once a quarter. There's just not enough people who sign up for those courses because they are kind of brutal, but it's a good course. I'm going to start out with something a little bit different. So right off the bat, one of the challenges that I have in this industry is that people use rule of thumb judgment when they're putting fire and gas detectors in, and I see it all the time. That detector in the upper right-hand corner is a state-of-the-art detector. I'm protecting its identity to a certain extent. Anybody who's ever used it or bought one or considered it probably knows whose it is. It is a very reliable company. The question I would ask you is, I'm going to pull up the technical data sheet on that detector here. And as you look across the headings, and you don't have to get into it, we're not going to read through this by any stretch of the imagination, but it's got a list of gas down the left side. It's got a default range, a selectable scale range, a resolution, two columns that are really uncomfortable depending upon which sensor you're using, the T50 or the T90, response time. That's something people don't even think about, is that the gas has to be there for a while and it has to stay there for a while before the detector goes into alarm. That's very challenging. And then the other thing is we read across here, so repeatability, zero drift, operating temperature, sensor type, sensor life, warranty classification. What I don't see is the size of the area that gas detector covers. What cloud size does it cover? It's amazing how many times, this happens to me a lot in a lot of different places. I'm not going to call out any part of the world, but it's amazing to me how often people literally tell me, Jim, I put a gas detector there. It'll detect a gas cloud within 5 meters of it. And I'm like, no, it will not. The only way it's ever going to detect a gas cloud is if that little red dot that just showed up here in the upper right-hand corner, if that little red dot, if that gas cloud is there long enough, then yes. And it's at a high enough concentration, then yes, it will detect it. But that gas cloud has to cross that detector. It has to touch that detector, and it has to stay there, and it has to be at a high enough concentration for that detector to go into alarm, period. That's just how they work. And so we have to keep that in mind. So the challenge I face is that people tell me all the time, hey, we got this, man. Gas detectors have an effective range. Leaks inside the range will be detected. No, that's not true. That's absolutely not true. We'll place gas detectors close to the leak source as possible, as close as possible. We'll put them like right on the machine. That actually a lot of times doesn't work at all, quite frankly. We'll put them on a 5 square meter grid. That one's not even listed here. That one's the health and safety executive's recommendation that came out of Aberdeen, Scotland. And that one is as a result of the Piper Alpha accident. And that's a legitimate, they actually used some science to come up with that number, because if you have a 5 square meter grid, the hypotenuse of the triangle of those detectors is 7 meters, roughly. I'm obviously rounding a little bit. But that 7, what happens is when a gas cloud gets bigger than 7 meters is that it basically, you have a really much higher risk of having a vapor cloud explosion, having a pressure wall when that thing ignites, having a pressure wall that's great enough to cause damage, all right, blow people off a platform, stuff like that. So they at least did the research to come up with that. Here's what's really interesting. Historically, over time, what they found out is that there are a whole bunch of platforms at sea now that have a 5 square meter grid. People still call us and say, hey, you can do anything you want. We don't care. Just put them on a 5 square meter grid. And we're like, well, can we discuss it with you? But the problem that they're having is that they don't detect even half of the gas leaks. Think about that. At a gas leak, and 50% of the time, if you were driving down the road and your brakes didn't work 50% of the time, would you be comfortable driving that vehicle? So these are things we have to think about. place detectors for dense gases near the floor and buoyant gases at an elevation from the location. Well, yeah, it kind of makes sense, right? Specific gravity, we're going to go with that. But did you know that there are times when very buoyant gases do not rise? There are times when very dense gases do rise. So it just isn't exactly that. And so the challenge we have is that there are a whole bunch of people do this and they do it, unfortunately, poorly. These rules of thumb are available, but they almost always fall short of optimal design. Basically, you get into situations where I literally did a presentation like this yesterday for the ISA in Kansas City. And at the end of the presentation, somebody said, Jim, can you just tell us where to put the detectors? Do we need to put them near the roof or, near the ceiling of the building? Or can we put them down near the floor or knee height or nose high or wherever? Where do we put them? And I went, did you not listen? No, you can't make that judgment. And I'll show you why here in a little bit. Results can be ineffective. They also can be very expensive. At the end of the day, if you have done the engineering based on a design basis and you have determined what hazard you're going to prevent and how often that hazard is going to exist or detect in this case, then you've done the right thing. You've at least done the science to prove that you're putting them there for a good reason. And we're going to go through that. So real quick definitions, fire and gas systems. This is really kind of cool, right? At the incipient stage, we want to detect as reliably and as quickly as possible a gas cloud, a gas accumulation, and if there's a fire, a fire. So we don't want to wait until it gets to be big enough that everybody can hear it and everybody can feel it. All right. So at as close to incipient stage as possible. That unfortunately makes us put gas detectors, when we don't do the science, too close to the leak source. Fire and gas mapping is kind of new to people. People don't really talk about this very much. They're beginning to. I know they're beginning to because people from places like China and Singapore and Australia and New Zealand and the Middle East, they all contact me. Africa, even places in the middle of nowhere, Africa, countries I actually never even heard of, these little bitty slices of countries. They call on the phone and they say, hey, we want to talk about fire and gas mapping. It's awesome. So word is getting out, and I'm not wasting my time doing this. So basically, fire and gas mapping is the engineering process and analysis methods to verify a proposed or existing fire and gas detector layout meets or exceeds the requirements, the performance targets to minimize the risks, to mitigate the risk, if you will. You're never going to get 100%. You drive a car down the road, everybody does all over the world now. You drive a car down the road, every intersection has a risk calculation on it. There is a risk to driving through an intersection. There is a risk to driving a car. The same thing's true about this type of stuff. So what we're going to try to do is minimize the risk as much as possible and at least make it as safe as driving a car. And then fire and gas system effectiveness, this gets into a weird place. And this is kind of how all of this started, was process safety people who were doing like SIL calculations and stuff, safety integrity level calculations for certain safety functions to figure out whether or not they were reducing the risk enough and that their probability of failure on demand was low enough that they would, they could trust that this thing was going to work to keep this stuff in containment or to keep the process working correctly. They said, hey, we kind of like to apply the same idea to our fire and gas systems. And so some of the rules do apply, but using exactly the same idea and trying to analyze it the way that they were analyzing the other stuff would cost millions of dollars. It would be very expensive. No one would ever do it. So as a result of that, I'll get to that in a minute, but as a result of that, the technical report that working group was created and that technical report came out. It's working group 7. I'll talk about it in just another slide, I think. Okay, so detectors. Difficult to determine the risk, detector array, the mitigation system, often implemented using the stuff we've been talking about, very inconsistent. It's amazing how many times we'll go find a process and then somewhere else in the world, there is a place, believe it or not, not too far from where I'm sitting right now, where, not on our site, we're in a Class A business office building. We're consulting engineers. We don't have to sit out in the field too much. Don't get me wrong, I have FR gear and hard hats and steel-toed shoes like everybody else. But there is a place where on one side of the road, one company owns a business, and on the other side of the road, another company owns and operates a business. And one side of the road, their business, they're very identical processes, very similar processes. They have very few gas detectors on the site. And on the other side of the road, they have a lot of gas detectors. And strangely enough, the guys with very few detectors want less, and the guys with a lot of detectors want more. And so people, a lot of times I don't go into any detail about this, and I just say, isn't that odd? And they're like, well, which one's right? Well, neither one's right, actually, because the ones who want more don't even know why they want more. They just want more. And the ones who want less don't know why they want less. They just want less. And they're usually motivated by budget, maintenance, time, whatever it is, right? And so it's interesting how we get into these weird situations. So historical problems, I want to talk about this. So there's a reason why there's diagrams on the right-hand side. So I just popped those gas detectors up. And the particular, this is actually a real world thing. This actually, I got on an airplane and flew to Houston and drove down the shipping channel towards the coast and went to a facility and met another Navy nuke, right? So I used to run a nuclear power plant on a submarine for 9 years for the Navy. And I met another Navy nuke, a guy who actually sat in a chair in the very same chair that I sat in to start up the nuclear power plant on that submarine for the very first time, because I built the submarine with the shipyard in Newport News. He had come years later and sat in my chair. I thought that was so cool. But what happened was he's working at this facility as an engineer, and he's part of they don't own the equipment, they're the operator. And so he's an engineer on the operations team, and somebody came in and they said, hey, from Honeywell, actually, and they suggested putting some detectors on this process, upgrading the detectors from the old bead bed detectors to new modern technology. And so the customer agreed, and they said, hey, we got a part of the process we're really worried about. It's this real high pressure part of the process, and we do have leaks with it periodically, and it's kind of scary, and we want to detect that. So let's put those brand new detectors right on there, replace the old ones. So they did that. And, they were kind of happy with themselves. And then lo and behold, they had a gas leak one day, and the gas leak basically happened, and none of those brand new shiny detectors alarmed. And the engineers, they just stood there going, well, the old detectors we had in the facility all went into alarm, but these new ones didn't alarm. And so take the new ones out and put the old ones back in. And they called the people who basically said, hey, here's the detectors, and helped them out with the process and sold them to them, and have been very helpful. So those people came out and they tested all the detectors, and they said, there's nothing wrong with the detectors. They're working perfect. And the owner of that company called me and said, Jim, I got a problem. And so we went down there, and what happened was the gas leak occurred in a way that it shot right out between the detectors, and it missed the detectors. Not only did it miss the detectors, but it entrained, using a Venturi effect, because of the way the leak happened, it actually entrained fresh air into the stream around it. All right, so it's pulling fresh air as this high-speed jet is shooting out between the gas detectors. It pulled fresh air in across the detectors. So it seemed like a good idea. This particular company that owned the machinery was like, no, we put 4 detectors on that machine, on that skid, on that process, whatever. And so they had a prescriptive design that they thought was adequate, and in reality, it didn't work at all. And so the right answer is maybe the detectors are a little too close. Maybe the detectors need to be moved. Maybe we ought to just model this thing and figure out exactly what's happening. All right. So, and unfortunately, no one had done that. They just made some assumptions, those heuristic things, rules of thumb. The other thing that happens is things happen, right? So one of the really weird things, we had done a fire project for a company. And I don't remember, I think it was 2 years later, they called us and they said, hey, your fire detectors that you recommended, where we put them and everything else, they're going into alarm. And we're going to have to make some decisions. We're going to have to basically, all the automatic functions are going to have to be turned off because they're going into alarm way too often. And so we put a guy on a plane. He flew halfway around the world, showed up at the site and went, "Hey, when'd you replace all your valve tags with these nice new shiny tags?" And they're like, "What does that matter?" And he goes, "Look at them, man. You can see them flickering in the wind." I just had a call from a company down in Texas somewhere, and they were having the same problem. The guy's like, "Hey, certain times of day on certain types of weather, our fire detectors are going into alarm." And I'm like, "Yeah, it's a brand new site, right?" He goes, "Yeah, all brand new equipment, shiny, beautiful, beautiful process, beautiful metal." And I went, "Yeah, I know." And I said, when the sun gets to the right angle, it's reflecting, and you have IR detectors that are detecting the actual reflection as a heat source. And so, but the problem is that we make really bad decisions. And in that particular case, I'm pretty sure the customer, they didn't hire us. I'm pretty sure the customer, just based on his conversation with me, decided to actually disable all the automatic functions and make an operator function to actually initiate the mitigation system. So on a fire alarm, he's going to look out the window, get on a radio, whatever, and make a decision whether or not to do the shutdown and initiate the fire control system. Okay, so I mean, that's not horrible, but it's not really based on anything other than that rule of thumb type thinking, which gets us into big trouble. So we go to regulations, standards, recommended practices, and unfortunately, they tend to be general guidelines and don't do a good job. Process safety management is much more focused on the left side of the bow tie, on the preventative safeguards. They want to keep stuff in containment, as opposed to mitigative safeguards, which are on the right side of the bow tie. I might explain that later, but all right, so there's a different way to look at it, right? So we have a process, it's under control, basic process control system, prevention, usually an SIS, sometimes basic process control system could do SIS functions. And then once we have a release, then we have a mitigation problem, right? So the IEC 61511 is focused on prevention, and the same ISA committee, the ISA 84 committee that originally created the ISA 84 standard that OSHA approved, that standards body created a working group. I'm on working group 9, which is cybersecurity for process safety systems. Working group 7, there are other people in this company that know much more about this than I do that are on the working group 7 committee that created the technical report 8407 for mitigation. But that's how those things are differentiated, right? Kind of clear in this picture. It makes a lot of sense. How we got to this point is OSHA basically said, hey, and I this kind of goes on all over the world. It's not always as defined as it is in the United States. In the United States, we have this government body that basically says, don't kill your employees, called OSHA. And it doesn't say it like that, but if you read between the lines, it's what they're saying. All right, so they have requirements for preventing and minimizing the consequences of a catastrophic release of toxic, reactive, flammable, or explosive chemicals. Don't kill your employees or the people who live outside of the fence line. The ISA 84 committee created the original process safety standard, which it's called the Application of Safety Instrumented Systems for Process Industries. The OSHA basically looked at that standard and said, they actually wrote a document that says, hey, this is a very good way to follow process safety management. In 2016, the IEC basically, it became the 61511. We used the IEC number because they're international, and instead of just using a U.S. number, the U.S. agreed to it. There is an anti-ISA 61511 standard, and there is an IEC 61511 standard. They are word for word pretty much identical as far as I know. That ISA 84 standards body in the U.S. created the Working Group 7, which released its first document, was formed in 2006, released its first version in 2010, and then revised it in 2018. If you search, I think on chemical engineering, I wrote an article about what's the difference in 2018 from 2010 that might be interesting to you. So the technical report is like recommendations from, if you follow the API, everybody has different names for this, but they're usually called something like technical reports, recommendations, recommended practices, something of that nature. It's basically a group of experts sitting out and saying, I've been on these committees for the American Petroleum Institute. It's a group of experts sitting down and saying, okay, what do we recommend is the right way to do this? And so that's what the technical report is. It's informative. It's not mandatory. Should be used with other good engineering practices, especially those applicable to fire gas system installations. Expects an understanding of the hazard and risk analysis that are done in the 61511 standard. It describes performance-based design. I just realized something. I'm eating up clicks here with a camera on that you can't even see. Describes performance-based design to address the risk of loss containment. It provides examples for how to do qualitative, quantitative, or semi-quantitative and fully quantitative analysis. Fully quantitative is a little painful. I mean, depending upon the facility, site, and the hazard analysis, quantitative can be really a monster. So there are semi-quantitative methods and qualitative methods to make that a little easier. And when you move from quantitative to semi-quantitative and even to qualitative, you got to be careful that you don't become less conservative. You actually need to become more conservative in the semi-quantitative state, and then even so in the qualitative state. When you move out of that, and you're starting to get into qualitative, unfortunately, is sometimes a little wishy-washy. It's what people feel. So you got to be careful there. But it goes into a lot of detail about how those things work. It addresses detector coverage, very interesting, safety availability, and mitigation effectiveness. Those all sound like good things for fire and gas detection. It recommends periodic assessments or audits to ensure system effectiveness. Okay, that's kind of a really good idea. If the stuff's been sitting there running for 20 years, we probably ought to be checking it, make sure it's okay. Did we add anything to our process in the last 20 years or take anything away? Is there a truck sitting somewhere? Did we put in a road we didn't have before? All those kinds of things we got to think through. Have we changed? Have we added obstacles? I'll give you an example. Another project we did was a fire and gas mapping project for a customer. And they called us one day and they said, hey, your stupid fire detector array's going into alarm again. And sure enough, we went out to the facility and we stood there and went, hey, when did you guys add that flare stack over there in the valley beside this plant? They're like, what are you talking about? They go, well, I'm pretty sure looking at that detector that it's pointed kind of where it could see that flare. And they went, oh, we just added it and just turned it on in the last few months. Like, you think that could be the heat source it's seeing? And sure enough, it could see that. When the flare shot up really high, it wasn't part of their process. It was an adjoining process. But when that flare, doing its job, but when that flare lit off, fire detector went off. So things change at our sites, and we got to take that into account. And just like we do with our safety instrumented functions, we need to look at it. Doesn't replace any safety instrumented functions, never replaces them. Don't do that. It is consistent with the principles of the 61511 standard. It recognizes that a fire and gas system is not designed to prevent a loss of containment. It's designed to reduce the severity if containment fails. And then I really like this. We wrote this. This isn't in the standard or anything, but it demonstrates how to examine the hazard and risk. We wrote this for an article, I think originally for a post on our website. And then I've been using it because I really like the way this works. Instead of going through all of the 11 steps of the technical report, it just kind of summarized, says, hey, you need to examine the hazard and the risk. You need to establish a performance requirement. You need to design a system to meet that. You need to assess that it does meet it by checking its coverage and checking its effectiveness. So pretty cool. All right, so let's walk through that. Well, it's interesting. Certain buttons work and certain ones don't. Okay, so before you even start, so the very next slide is going to be about doing exactly that stuff. I apologize, there's two slides here. Before you do that, you need to have a philosophy. So people call us every now and then and they go, hey, we need to do that fire and gas mapping thing. And we're like, okay, so before we get started, how are we going to do this? Do you have a specific amount of gas? Do you have a certain size fire? Do you have, you know, and they're like, no. Okay, so what's your risk criteria for your site? And they go, okay, so well, a real common answer is 1 times 10 to the minus 4. All right, that's good. So has anybody ever come up with a philosophy or a strategy for like toxic gas detection or for, I don't have the other one, or for a fire, right? So toxic gas detection is good. I go through a lot of, and so there are things here you can see, right? So there's immediately dangerous to life and health. They want 10% of that number as their detectable number. That may or may not be a right number. It depends on the gas. Do we need to have personal protection gas detection limits? How do we, where do we make those decisions? And then as I go through these safety evaluations before I'm allowed to walk down a lot of sites, I'm amazed how often no one ever says to me, do not enter an area where a fixed detector is in alarm. No, let me rephrase that. I'm amazed that no one's ever actually told me that. Think about that. I've gone into facilities and gone through, I went through a safety course that lasted an entire, 2 days in Italian. And I had to take the test in Italian. I do not speak Italian. I do not read and write Italian. It was very difficult. I'm not going to kid you. But because I've done this 100+ times, I could figure it out. Do not enter an area where a fixed detector is in alarm. If your personal protection detector goes into alarm, move, get out. Wouldn't that be nice if that was actually in everybody's safety briefing? I had some guys give me a phosgene tag one time. I went into a facility and they gave me a little tag and they attached it to my FBAR gear. And I looked down at it and I went, that tag changes color when it senses phosgene gas, right? And he goes, yeah. I said, so that's for the responders that are coming to pick up the dead. And he looked at me and he goes, huh, never thought about that. And I said, by the time that changes color, I've taken a lung full of phosgene and I'm dead. And the guy goes, well, that kind of sucks. We just don't think this stuff through. We got to be better at this, right? I worked on a submarine. We couldn't run away from a hazard. Think about that. On a submarine, you can go, oh, that's bad. And you run 12 feet and then you turn around and go, I need to deal with that bad thing. Because there's nowhere to go, right? And so we have protection equipment, we have detectors, and we have trained responses to everything. And everyone on the boat to get qualified to work on a submarine has to be submarine qualified. And it takes a long time. It's hard because you've got to learn all this stuff. It's not a 1 hour or a 2-day safety briefing. It's 6 months of every spare minute of your life learning how to keep alive and keep the rest of people on the boat alive and keep the platform functioning. So yeah, put those things in your safety requirements. So our process, this is why you tuned in today. I'm sorry, I took 30 minutes getting here. I think it's good content though. So you're going to examine, you have a philosophy, all right? So I skipped the philosophy part. So you have a philosophy, you know what your tolerable risk criteria is. You're going to evaluate your unmitigated risk. So you're going to go through an event tree like this, and you're going to come up with a number. And this number is 6.52 times 10 to the minus 3. Okay, reasonable number. I'm looking at the number to the right. Oh, that's the corrected number. I can't believe that's actually on that graph too. I'll show you that in a few minutes. All right, so you're going to go through this, and you're going to figure out, how many injuries do I have, how many fatalities, things like that. Those are going to add up to numbers that you can see down there in the bottom in color. And then you're going to know what your unmitigated risk really is for a particular area. You can't do this for an entire refinery. That just doesn't work. You're going to pick areas that are more important for whatever reason, right? Maybe an underwriter walked through and said, hey, why is this area got this many gas detectors? I think you need more. So you're going to do some evaluation to figure that out. All right, then you're going to establish a performance requirement. So based on everything you've learned to this point, you're going to go, okay, in this case, that's just wrong. We have I apologize, that number is just wrong. We have a 6.52 times 10 to the minus 3 risk. That's interesting. Something in PowerPoint's incorrect. That never happens, of injury or death. And corporate acceptable standard is 1 times 10 to the minus 4. 7.652 times 10 to the minus 2. Okay, that's worse. But I think that was for something else. A design fire, we're going to pick the one that they use. So this design fire comes up a lot. We get two radiant heat output fire ratings. We get 10 kilowatts per hour and 50 kilowatts per hour. We see those showing up all over the world in people's design philosophy. So the 10 kilowatt fire, the 1 foot by 1 foot, which is about 0.3 meters by 0.3 meters. And what they do is they pour, I think it's heptane into the pan, and it's a fire pan, and they light the fire, and they test the fire detectors to see if they can see it. So they move the fire detectors further away and to the left and the right and up and down until they develop a cone of vision for that design basis fire. All right. And once they have that, then they can give you that design criteria. We actually input that design criteria into our software. All right, so we ask all the vendors, hey, can you tell us what your cone of vision is for your detector for it's called the FM 3260 test, factory mutual 3260 test. And pretty much everybody in the world does that for their fire detectors. A design gas leak. So we see two real common ones. We see a 1/4 inch and an inch. So whatever an inch translates to in meters, and so 5 millimeter is about 0.2, and so I guess I'm not going to do the math. I will fail at this terribly. 5 times that would be somewhere around 25 millimeters would be about an inch, I guess. I'm guessing here. Don't take that to the bank. I think it's 2.54 centimeters is an inch. See what I do? Don't do that. But basically, we see a 1/4 inch and an inch pressurized gas leaks. This is why we have to ask questions, by the way. We ask questions all the time like, okay, so you have stuff in containment. What material, the material in containment, what phase is it in? Is it a liquid? Is it a gas? You got to ask those kind of questions. What phase is it in? What pressure is it under? What temperature is it at? Because when you have that leak, when it comes out of there, the temperature, the pressure, the phase, all of that is going to affect how that leak behaves. And people are like, well, Jim, man, it's hydrogen. Okay, is it hydrogen or is it liquid hydrogen? What do you mean? Well, liquid hydrogen will probably flash over pretty quick, but who knows for sure? It might depend on pressure and temperature you have it at. So it may come out and behave completely different than hydrogen behaves for the first few feet. Interesting to think about. Your LEL level. So what level do you want the system to be at? In this particular example, we used propane and butane, basically because they're similar gases, but they have a slightly different rating. So we ended up with 2100 ppm and 1900 ppm as the level we wanted to be at. And it's interesting because now what you have to do is you're not going to put in a gas detector for 2100 ppm and a gas detector for 1900 ppm. And you're not automatically going to put one in and just set it at 1900 ppm. What you need to look at is response times and everything else to decide what settings to put into that gas detector, and make sure that it will react well at 1900 ppm and won't give you too many errors at 2100 ppm at the propane requirement. So those are things you have to look at. You read through all the specifications of the detector and make those kind of decisions. A lot of it's based on something you're going to hear me talk about later called expert judgment, which is just lots of experience. You're, in this case, asphyxiant, 1900 ppm, so they want that to be whatever it is. Major equipment grading area. This is so most companies in the world today, when we ask them, do you have a grade in your philosophy, do you have a graded area requirement? This is very similar to an electrical area classification. If you have graded areas, it's like grade A is like class 1 div 1 electrical area, grade B class 1 div 2, and so on and so forth, right? So basically, the more coverage that you require, the greater the grade that you're going to put on that area, and the greater the coverage that's going to be required to prove that you can detect a gas leak or a fire and engage some form of mitigation. So that's how grading works, and that's probably enough on that. And detector alarm voting schema, yeah, a lot of people don't have this. There aren't a lot of people who do multiples, 2 out of n type voting structures for fire and gas detection, but it does happen. It is something that it drives us a little nuts because it's hard to get it right, and people are always cost conscious, and you got to put in multiple detectors so that in an area, so you're going to have at least 2 go into alarm, and it's kind of weird. And then what to do on alarm, I'm not going to go into those, but because it could be things like, do you activate or not activate? Do you dispatch automatically or not? Do you shut down building ventilation? Do you isolate? Do you depressurize? Do you de-inventory? Right? So all those things are real. So we're going to assess we're going to go into the next phase, and we're going to do it by picking a piece of major equipment. So in here, I picked the pumps. So I'm looking at the pumps, and I'm asking all those questions about the pumps. I'm going to, if this is an outdoor setting, I'm going to ask for what's commonly called the wind rose in aviation. Rose meaning ROSE, like the flower, because it kind of looks like a flower if you look at it. So it's commonly called the wind rose. Some people call it different things. Just say, hey, do you have the wind data? Do you collect? You can actually, sometimes you can actually ask the health and safety people at a site, and they're like, oh yeah, we collect the wind data. We have a wind chart for it. And so that's perfect, right? That's better than using the nearest airport, but sometimes we go to the nearest airport. What we're looking for outside is prevailing winds. Is there a preponderance of time when the wind comes from one direction versus another? Sometimes this looks like a big bow tie, because certain time of the year the wind comes from the south, and the other time of the year it comes from the north. And so, it could be different. I used to live somewhere where the wind always came from the west. And I had trees in the backyard that leaned to the east because the wind always blew from the west to the east. And by always, I mean like anytime there was a big storm coming, almost every time the wind was blowing hard, it was coming from the west and going to the east. That doesn't mean it didn't go the other way sometimes. It just didn't go there very often. And you can actually see that here in this particular wind rose the wind does blow in that direction sometimes. There's some energy going that way, but not very often. And what that means is the gas cloud has a preponderance of being up here because the wind's coming this way more than it does being over here. So that's a weighting that we use for that type of risk. The next thing we're going to do is we're going to model the gas cloud. So no rocket science here, Gaussian modeling. Our company uses DNV's FAST software, PHAST. There are other Gaussian model software out there. I will tell you that all of the software that we found that is relatively inexpensive or free does not work very well. And so sometimes you got to bite the bullet and spend some money to get the right thing. I hope we've been working on a Gaussian modeling system, but it's not easy. It seems like it should be, but for some reason it's given us some grief. Eventually, we hope to have a module in our safety suite that does Gaussian modeling at a minimum. All right, so anyway, there are other tools out there. You don't have to use the one we use, but the Gaussian modeling is going to give us some information that's valuable. If we're going indoors, we do something very differently. So I don't need your wind data indoors. What I need indoors is I need your heating and air conditioning and your ventilation fans or your evacuation system, whatever moves air in and out of a space. So, and then I need to know the space. So I need either a model of the space or a floor plan and some measurements of the height and the equipment that's in there that are the major obstructions, because I'm going to actually model that, and I'm going to use, instead of doing it in Effigy, which is our software, we're going to model that in a computational fluid dynamics tool that I'll show you more about in a few minutes. And we're going to model that leak and design the detector array a little bit differently. So one of the things that's in this list that doesn't show up here. Oh, and then we'll go down through all these things. I apologize. We're going to use standards, case studies, and experience, which in another presentation ended up being called expert judgment. And so my next slide will say expert judgment on it, right? So I grabbed those slides this morning, actually, about 8:15 before the presentation, and stuck them in here because yesterday when I gave this presentation and went into the expert judgment section, people were like, hey, that's really useful. So once we've done all that and we've picked where the detectors need to go, then we're going to assess the detector coverage using, and we do it using Effigy and outdoor Gaussian models for the consequence. Fire, you don't model for fire, you can pick a size of fire, a certain amount of energy. So a 1 foot by 1 foot pan fire that generates about 10 kW of radiant heat output is about a meter high and about 0.3 meters wide. So you can design that fire and, believe it or not, put it into the software. So and I'll show you how to do that here in just a second. And then computational fluid dynamics for indoor gas situations. Outdoor fire applications, just like indoor applications, I need to know the obstructions. So something like this pump skid right here is an obstruction, and fire detectors can't see through that pump skid totally. So I need to be able to model the obstructions when I'm doing fire. And when I'm doing computational fluid dynamics, I also need to model the obstructions because they affect the way the gas and the airflow works in the room. And then I need to basically assess the effectiveness of the system that I did. So let's just do expert judgment real quick, and then I'm going to do a real quick demo. So expert judgment. Gaussian model is going to give me length, width, and it's going to give me an offset. See this little offset right here? In this particular case, this is the amount of time it took propane or butane to reach the ground from the leak source. All right, so if that pump skid leaks, the amount of time based on the pressure and temperature in that particular skid, the amount of time it takes for that gas to fall to the ground and actually touch the detector that I'm going to put at about a foot off the ground is going to take that distance. All right. And so the software does that for you automatically, which is very cool. You put in, pressure and temperature, what type of gas mixture, and what size of hole, and it does all the calculations for you, which is fantastic. So we're going to model that. I'll show you how to do this in a second. We're going to model that, and you can see these little gas clouds here. What they are is we've taken that model and we put it into the software and we've wrapped it around. Oh, there's the little offset. We've wrapped it around the source, and it has automatically said, hey, there's an offset. So I need to put that gas cloud out a certain distance away from the source because it's going to take time to get down to the detector. And then you can wrap it around anywhere from, I think the variables are 32, 128, and 720 times around an object or a leak source. Okay, that's pretty cool, but that didn't take into account wind. So let's take into account wind. And then I'm going to overlay the plot plan so I can explain which way the wind is blowing. So the wind is blowing this way, the preponderance of time, which is basically coming from here and going through the site that way. So if I look at this, you'll actually see the arrow goes the other way. The cool thing is now what you see is yellow is a greater risk than green and blue. As the colors get cooler and cooler, the risk quantity goes down. That's actually in this little chart right here. So yellow is actually pretty high risk. It's somewhere around 5 times 10 to the minus third, I think, minus 3. So anyway, that's this is what they call scenario coverage mapping. All right, and so we're doing scenario. If we do geographic, then geographic is, and I'm just showing gas detectors here. So geographic is I'm going to put I'm going to put my gas detectors in on a geographic model or grid or whatever, right? It could be on a 5 square meter one. When I did this particular one, I put them in trying to do one thing and then used it for a different example. But same idea. So geographic, I've got a gas cloud now, right? I have a model gas cloud, and I don't want it to be bigger than 7 meters in diameter. So let's go with a 5-meter gas cloud. And here's the problem. We don't know how it's going to move or react in the facility. All right. So will it actually, how often does the, and this is an offshore facility, this is the Wellhead Bay. And so, and it's actually a place where leaks occur on a regular basis. And so it's somewhere people get really kind of crazy and carried away with, rightfully so, about gas detection. And so you got to really think this through. It takes a lot of experience to get it right. And it's challenging, but you know, that's a geographic challenge that you have to live with. So these are kinds of things, different types of analysis. We build inside or even outside. We've got to also take into account the gas cloud. So we have these momentum problems, right? So when a gas cloud actually basically comes out here, this one builds up a little bit, but it's got momentum. So it's shooting out. That momentum eventually loses its energy because of the air it's pushing against, and it begins to pancake out. All right, so that's something to think about. The other thing that happens is you can have a buoyancy effect. That could be because of a phase transition. It could be because of just the fact that the gas is hot. So eventually it's going to come up. So depending upon the amount of energy in the motive force in the release, it may stay very parallel to the ground for a while before it becomes buoyant. So all those kinds of things you got to take into account too. The other thing is you have, like outside, you have this, okay, the release is going the direction of the red arrow, but the wind is blowing the direction of the green arrow. So at some point, the gas cloud is going to lose momentum, and the wind is going to take over and push the gas cloud a different direction. So all those things go into that quote unquote expert judgment classification. The other thing is, remember I was talking about this offset here. This one doesn't have an offset. As a matter of fact, this one actually has a number that's positive, and that cloud actually passes through zero just a little bit. All right, so that's pretty interesting. And what people do is they go, okay, so this is this is the flange on that machine I'm worried about. So I'm going to put a detector right here beside it and right here beside it. Well, you can see it's very easy to get that wrong. You've got 4 sides. So how do you know exactly where to put it? And are you going to be able to put it right in the gas stream, and will it detect? In reality, what happens most of the time is it doesn't. So sometimes backing the detector off is the right idea. Here's a perfect example. We actually did this for real. We did this. I am actually not allowed to tell you who we did this for. I apologize. But a typical geographic coverage would tell you that you had 100% coverage because this thing was right in the graded area. All right. So the graded area around there, whatever size graded area you put in as your model, some people put in 5, 7, 10 meters, depends. So you have this graded area, you place your detectors in a graded area and you go, yeah, look, I got 100% coverage because I'm doing geographic coverage, right? See right here, a graded area is yellow, and I have a detector right in the middle of the graded area. So I have this yellow sphere around here, which you can't see, and there's my detector. And the problem is that in a scenario model where you actually model the gas almost never exists where that detector is at a level that could be measured by the detector. So it never goes into alarm. And in reality, that's what's happening. It happens a lot. All right, let's do something really weird here. I'm going to actually just hit escape and minimize this window, and I'm going to jump you into our software. So I'm going to go in and log into the system as me. And I can see a lot of projects because we've been given permission to see them, to work on them. And so ignore everything you saw in the left-hand column a minute ago, if you did see it. All right, and I know this is going to be recorded, so people are going to be able to go into it. So I have some finished solutions here. Let me just pop into one real quick. I'm going to do fire detectors from the beginning. I have input my graded areas. I have input my wind data. I have no fire or gas detectors. However, I have an equipment item called a 3D model, which I'll show you now. Let me take a sip while this is loading. The plot plan is the first thing that shows up on the plane, and then the 3D model shows up. So this is actually a legit 3D model. Very cool. We can import 3D models. We're going to take whatever CAD you have and ask you if you can export it as a stereolithograph file and a .stl file. If you can't, there's a chance we can convert it. But yeah, so that's how that works. I'm going to go into, oh, I do have a stored location in here. Let me get rid of that. I don't want that. And my equipment items. So I'm going to do, this is fire first. Fire demo, no detectors in the system. So I don't need anything in here. I'm going to leave that alone. And I'm going to sit here and go, okay, I should have a graded area around these pumps. So this is P235A and 235B. So I'm going to turn those on. And I'm going to go here to my area grading and see if it's there. And sure enough, it is. So there's the area that the customer wants basically modeled fire detection around. I just noticed something. This isn't at the ground level. So I'm going to jump over here and I'm going to pop in here and put this in at 0 and hit update and go back because I don't need that artificial height for the gas detectors. That's what happens when you copy masters. It's good way. It is a good idea to separate these and not do gas and fire in the same graphic, which is why we give you the ability to do what I just did. You can copy projects and change them and get back down to a 0 plane now. So that's what I did. All right, so I need to put a gas detector there. And what most people will do is they'll say, hey, look, we need a fire detector, is they'll say, hey, let's put a fire detector right here and let's put it in on a pole. So we're going to add a fire detector and we'll add it at the selected surface. Wait a minute, I need to orient. Okay, I'm not sure what I'm doing. So let me right click here again and I can focus and I move that little magenta sphere into the middle of that. And I'm going to actually put that detector in now, a fire detector at the selected surface oriented to a focal point. That's it. Sorry, I actually do know what I'm doing. They're just days I have fun. I put in generic, and the reason I do that is I want to highlight the fact that you don't need to know what detector you're using right off the bat. These are all in here, and so if you work for one of these companies, great. Your company cooperated very well with us, and so here's an MSIR detector. We could put that in. Let me go back to generic. I don't want to plug any company, and we'll do MSIR. And we'll do a hydrocarbon because that's the only choice I have. And that particular detector, what did I screw up? That's interesting. Huh, I found a glitch in the software. Awesome. All right, we have something to go fix now. Let me go back to this detector. We'll go to hydrocarbon and we'll pick a sensitivity. I got to remember that. That's awesome. I don't think anybody ever did that before. All right, so this detector, we're looking at a 10 kW. This is actually put in up here underneath this little tool, the wrench tool, as a setting, but it has its, its stuff. It's not going to be at that height. We're going to put it up in the air. We're going to probably put it up in the air about 9 feet. So we'll put it at 3 meters. It means you're going to have a ladder or lift depending upon your company. That's going to make the detector point out at some really weird angle because we just moved it incorrectly. So I'm going to right click on it and tell it to orient again. And I'm going to orient back to the focal point. That was it. And now it's staring right down through there. What's really cool is I can pop in here and literally click on the eyeball and look at what the fire detector sees. All right, that's kind of cool. So that's not bad. And so it's kind of pointing in the right area. And what I'll do is just show you this real quick. This is where that information was coming from. So plume model, the plume model, and then I have gone in under default fire detectors and said I'm looking for a 10 kW fire as a default detector. That might be where my glitch was. So I'm going to run the fire geographic coverage, which is what I'm doing here. Now, so our software doesn't run on your computer. It's not even running on my computer. It's not running on the Mac. It won't run on a Linux. It won't run on Windows. It's actually running on Microsoft Azure in the cloud. So we actually built all our software to run in the cloud to take advantage of giant processing capabilities that are available in the cloud that you just can't have in a desktop or laptop computer. So when that's done, I've actually run a calculation now that shows me my fire geographic coverage. If I click on that, it said it was out of date. It wasn't out of date. All right. And I've already reached 80.6% coverage because I turned on plume modeling. However, I don't like where this detector is because I'm going to have to put in a pole. I'm going to have to put protection in. People are going to have to get a ladder or something, so expert judgment time, right? So expert judgment to me says, can I see the fire detector from over? Can I see that from here? And so what I could do is click in here and pick a point and say, man, I kind of like that. I can see that entire graded area outline right there. So let's go on top of this piece of pipe right here. And I'm going to store that location. And I'm going to right click on that detector. And I'm going to tell it to move to my stored location that I just stored. And there it is. Now it's up here. Now it's all oriented wrong. So first thing I'm going to do is open up the details form. And I'm going to say, all right, where's it at? It's at 6.42 meters because it's on the handrail. All right, so that's not right. I need it to be a little bit higher. So just for practical purposes, I know this isn't reasonable. Nobody could reach it at that height, but I'm just going to put it at 7.42 meters. And I'm going to hit update. Okay, that's kind of cool, but it's still pointing the wrong way. So remember, we can orient. So I'm going to orient back to my focal point. And then if I click on the eyeball and see what it's looking at, look what it can see. So I already have it set to high, so I know that's going to work pretty well. But before I run that, let me go over here, and I'm going to turn plume modeling off. We're going to go to point source, and we're going to do it like everybody else's software works, and we're going to run our analysis at that level. So I'm going to hit run. By the way, you can run all these at the same time. They run in parallel, so they get done really fast, which, again, wouldn't work on your computer. So here's my fire geographic coverage with that detector. Look at that range. It could, oops, sorry. And then back up far enough. Look at that range that detector can see. Now you can imagine why a tag hanging out here somewhere with a reflective thing or a flare over here might cause that detector to go into alarm. So there's a couple things we could do. We could point it down more. We could do, a bunch of stuff. I'm not going to do it. But now you can see that the shadow behind this is very real. So this particular area has a shadow. My coverage is, for that graded area, is fair, but it's not great. That's a grade C. And I have a 60.6. Yellow, by the way, is one detector can see the area. Green is two or more detectors can see the area. And red is no detectors can see the area. So my coverage for that grade C area is only 60%. All right. Now, what I can do is go back up here and say, look, I want to model the fire. And so instead of doing plume source, I'm going to do 0.3 meter width, 1 meter high, that 10 kW fire, and I'll hit update. And I'm going to rerun this program real quick for fire geographic coverage and just hit run. Now this will take a little bit longer because it's basically analyzing little 1 inch by 1 inch cubes to figure out whether the detector can see that area with that radiant heat in it or not. Enough of it. All right, so what it's going to do is it's going to, without removing any of the obstacles on the real piece of equipment, it's going to tell you whether or not it can see that. And so it's saying, hey, unless you have a fire like right in here or right behind here or behind that obstacle, we can see that fire 81.4% of the time with that one detector. All right, so that's why some of these features, the things that we built, we wrote, by the way, this uses nobody else's subset or modules or objects of code. We wrote all this code ourselves. And we did it very deliberately because we couldn't find an engineering tool that did this well enough. All right, so let me jump out of here. Let's take a look at gas detectors, and then we're going to take a look at computational fluid dynamics. Now, I'm not going to do a live demo for that. Same thing. In here, I've got grading area, wind data, and I have it set at 0.3 meters, which is the right height that I need to be at for this gas. So let me jump into the 3D model. Now this is just a copy and paste of the other one. I did them before we started this morning so that I would have two fresh ones to begin with. So in here, what we're going to do is we're going to do gas detection, except I need to actually turn on the equipment. So let's do the same area. We're going to do just that propane pump, and then I'm going to turn on something else here. You can't really see it very well, but I'm turning on the gas scenario. I need to move this around and make this bigger, but I'm going to try to be efficient on my time and not mess with stuff I don't need to mess with. So let's go into area grading again, and sure enough, the grade's going to look exactly the same because it is. I don't remember what grade it is. It'll tell us here in just a minute when we do the analysis. So my first reaction is we'll just do geographic, right? So let's put some gas detectors in here. So I'm going to zoom in real close. Now I have a parallax area here. So let's jump to 2D for a minute and take a look at it. So I probably need to put a detector right about right there and maybe one right about right there. So that's kind of a way to look at it. So my focal point keeps moving around, so let's fix my focal point right there. And now I can zoom around and use typical AutoCAD type mouse and key movements. So, all right, so I want to put a gas detector right here in the middle of that one. So I'll add a gas detector there, and I'll just put a point gas detector in. You can see we can put in other stuff too. So we'll put in gas detector number 1. No magic. Got a little parallax on my height, 0.3. I have put in a critical cloud and 1900 ppm already as my defaults so that I can do this a little faster. So I'm going to hit insert. That's, by the way, up here underneath of this bolt, right? What would be really cool is I could jump back out to the I button, to the info button for the project, and I can actually do copy and paste these with an offset. But that actually takes longer than I care to admit. So I'm not going to do that unless I have a big project and I'm trying to put in a bunch of these. I'm not going to do that. We could put a gas detector in over here, but let's just run it without doing that and see what happens. So gas detector geographic coverage, that's what we're doing. And scroll down and hit the run button. So now we're doing completely different type of analysis. And I'm going to come up here and I'm going to click on gas detector geographic coverage. And it's going to show me what kind of coverage I have. Okay, that doesn't look great. Let me hit refresh here. Okay, so it's up to date. The yellow is covering 67.9% of the area. That's not adequate. So I'm going to put a gas detector over here too. And we'll put a point gas detector there. We could put in an open path. By the way, we do sonic. We also do gas cloud imaging, which is done with computers. So this is gas detector number 2. Got to adjust that again to 0.3. Leave those at the defaults. I'm going to hit insert. You see the little gas detector pop up right there. We'll go ahead and hit run. Oh, by the way, this is doing not only the judgment, analysis of where to put them and everything else, but it's also assessing the coverage for us. And you're getting to see that all in real time. I'm watching my clock. I'm trying to be mindful of the fact that I said I'd get this done in 90 minutes. So I'm going to get out of here in just a second. So I recycled this and now I have pretty good coverage. So I have 66% covered by one detector, 33% covered by two detectors, at least two detectors, and less than 1% uncovered. All right, let's leave that alone. So now what I want to do is I'm going to go into that equipment. So I'm just going to click on the equipment. And here I am. I've got, this is in here. The grading's in here. It's grade C. So I only have to get to 60% coverage. We could change that here if we wanted to. I'm not going to do fire scenarios. Fire scenarios are jet fires, all right? And jet fires depend on the gas and all that kind of stuff, right? So I'm going to go in here to a scenario that we've already put in, and I'm going to explain this to you real quick. So here is the length of the Gaussian model. Here is the width of the Gaussian model. And here is the height that we're going to put the gas detectors at and the height that we ran the Gaussian model at for one of the slices, the one that makes it look like that weird oblong, I don't know what that shape's called. I'm sorry, this is actually the location, the height that it was run at. It's 52 meters long, 30 meters wide. Frequency came from my hazard I didn't show you how we do frequency calculations. So basically, we look through all the equipment and sum up the chance of having a leak on that piece of equipment. And that came out to 3.2 times 10 to the minus third. And then this hazard should be set at, actually, the gas cloud we created was at 4,200 ppm. So we're going to leave it alone because that's actually it. And the offset was minus 2 meters, meaning that it takes 2 meters for the gas cloud to get down to a foot off the ground to 0.3 meters. Okay, so that's kind of cool. That's what a gas scenario is. I didn't really change anything. There's one in here for each one of these pumps, all right? So what we're going to do now is, let's just come up here real quick and we'll look at the general information. So everything's set in meters, default icon. Gas coverage can be volume or area. There's some mathematics involved in that. We can do point source or plume for fire, but we're not doing that. So we're just going to leave this alone. We're doing volume calculation. That's fine. And we will, oh, the default gas detector. I need to look at that. So I told you we were going to use the lower gas. So we're going to use 1900 ppm. And we're using just a generic detector. You can see there are a lot of gas detectors in here. And we'll hit update just in case I changed something. I don't think I did. Okay, fine. And let's go run. And now what we're doing is gas scenario coverage, and the gas geographic coverage is still up to date because I didn't move any of the detectors. So I'm going to hit run here. And it does this pretty quick, actually, which is kind of cool. And so geographic coverage is still the same. It's going to get exactly the same result. Let's go down here and let's look at my residual risk and see what that looks like. So, wow, that doesn't look right at all. Things look really strange here, actually. I see all this yellow area, which is like 5 times 10 to the minus fourth to 1 times 10 to the minus third. And then there's some orangish area, which is starting to approach 5 times 10 to the minus third. And I can see the cloud shapes here. What's different? What's different is we're not doing geographic anymore. We've moved to scenario. So the geographic coverage, which basically said it was in essence 100% covered, in scenario coverage is only 20.2% of the gas clouds are covered. So in fact, the gas is almost never actually in this graded area in scenario coverage. Let's go to 2D. You can see this much better. So what's happened is the wind is blowing this way the majority of the time. The gas leaks are occurring from here or here, and you can see the gas clouds, right? They're all over the place. There is gas cloud over here. It's a less risk than a chance of the gas cloud being over here, but the chance of a gas cloud being in here is almost nothing. The gray area is nothing. The green area is in this range right here, around 10 to the minus fourth, so very rarely there. These gas detectors are in a horrible location. They're too close to the source. I've heard that before somewhere. So where would I put them? Well, I might put them over here. So let's add a stored location there. What did I just do? Oh, I'm sorry. Stored location. I'm gonna get rid of that one because let me just go down here and I'm gonna hit clear all. And I'm gonna come up here and I'm gonna put a gas location. I'm gonna store that location right there. And I'm going to, sorry, I forgot to use my mouse. I'm going to move that one, that gas detector, it says gas detector 1, to my stored location I just put in over there. So let's rerun the calculation and see what that did. So gas scenario coverage, geographic coverage has changed because I moved it out. So let's rerun that one. And then I'm going to stop doing this and move on because I think you've seen enough of what this does. So I'll hit refresh, and just by moving that detector over there, I'm now detecting 46.5. If I go back to geographic, I'm not even in the area, so this doesn't count. All right. So now I've got, matter of fact, this is actually out of date. Let me hit refresh. I'm looking at it going, that's not right. So this gas detector has a bubble around it for the range that not for the range that a gas cloud could be detected. It has a bubble around it for the design of a gas cloud. What that means is if I had a gas cloud that size that came in here, I would probably be able to detect it. Geographic coverage is actually pretty spotty because if we think about it, we're basically guessing a lot of things. And when we look at the difference, we can see that, okay, geographic kind of makes some sense. And now I look at this and I go, look, I can see some clouds here. Maybe if I just take this detector over here a little bit and I'll hit a stored location there and I'll right click on it and tell it to move to the stored location. And I'll move it to location number 2. And I should right click on it because I really need to put it at 0.3 meters and I'm pretty sure it didn't do it. I think the software knows enough to deal with that, but because it did over here. So let's go ahead and hit run. And we'll rerun everything. Yes, I am a fast talking guy. I apologize. I know it's hard to do this. To watch it, it's hard to do. Look at that. Now we're at 65.7% coverage. So that's interesting. So probably need a detector over here too. So geographic, in this case, might get me less detectors. And I'll just bury my head in the sand and say, I really don't need it. Let's look at what a complete project for gas detectors look like. Oh, I don't want to run that. Everything's current. Let me just jump over here. This is one where I turned on all of the hazards that are available here. You can see there's gas detectors in a few locations here. There's actually 1, 2, 3, 4. I think there's 5 gas detectors. Let's look. 1, 2, 3. Oh, I put in some decent ones. Awesome. All right. So let's go down here and look at my residual risk. Look at that. So with a very unusual looking array of detectors, I have 84.2% based on the probability weighting that the wind is causing those gas clouds. Right? And so you can do this also without doing gas clouds or without putting in the wind. So here is actually where I did one with no wind, just so we could see what it looked like. I'm going to flip it to 2D because it's easier to see in 2D. I should have clicked on the 2D icon up here. We keep threatening to take the 2D icons out. My residual risk. So you can see what it looks like when you don't put in what am I looking at here? Give me just a second. There's no gas detectors. Is there wind data in this system? Duh. I'm sorry. It says with wind data even. Sorry. Operator error. My apologies. Unfortunately, until this is done, I can't get the update. I can't force it to do the other. Again, I should have clicked on something else. I should have clicked on one of these gas icons up here, but you can see what it does is it makes it really uniform around here when you don't have wind data. So you could do it this way and ignore wind data. If your wind data is untrustworthy, you might want to do it this way. All right. Enough of that. Let's jump back to the Parallels desktop. And I'm going to put this back into play. All right. So when we move inside of a building, and this is very common, there's a mixture, sometimes even offshore platforms, sometimes part of the process is inside of a very confined space. Some people might call that a building, but very common to see part of the process in a building, right? Like at a natural gas pumping station, part of the process is typically in the building, part of the process is outside of the building. So you end up doing both for a site. So what we use here is computational fluid dynamics. We actually use software called Fire Design Simulator from the National Institute of Standards. This is a very difficult to use software. We use a third-party tool. I do not remember the name of it. On top of it, that allows us to model it and execute it well. We run this on a cluster. We can't give you access to this. This is what we do for you. But we run this on a cluster of Linux computers that we built in our server closet here in our building, in the building I'm in right now. So we have a cluster of Linux computers that's run by a master. Those computers compute every basically square inch or square few inches or square foot or whatever. So, if we do a 5 millimeter quarter inch leak, we could do every square inch, do 20, 25 millimeters, whatever. And so what we do is we model the isosurfaces, and we model basically slices through the system to tell us what's going on. So we create the room or the space, we create the intake, the exhaust systems, how's air getting in and out. This is airflow, by the way, up here in the very top one. The next one is a small leak, and it's a small leak early. This is the small leak late. So basically after a certain period of time, this is what the leak is grown to. This is a 25 millimeter leak. My math actually worked. 25 millimeter leak, about a 1 inch leak early. Very quickly, the gas cloud forms like that. This is that same leak. It's actually methane, and we've actually done a slice down the center of the room, right down the center of the equipment to see where the gas clouds are and to determine where we're going to put the detectors. In here, we have to analyze stuff a little differently. So these are just some charts that I took out for gas detector time to alarm based on where we put a gas detector. So this is based on the concentration of gas. It's based on the location that the detector is going and the specifications of the detector. So if we put a detector, for instance, right here or up here near the ceiling, it's going to take a certain amount of time to go into alarm. And we're going to measure that for each detector that we put in and figure it out, all right? And so things get different. Sometimes we do asphyxiation, and we're going to measure the loss of oxygen. So if we're pumping nitrogen into a space, we might want to measure, instead of trying to measure the gases that could come into a space, we might want to measure, because if our risk is asphyxiation, that's what we want to measure, right? Do I have enough oxygen in the space or not? And so, unfortunately, there's time to alarm here. Look at that. I mean, that's real time, right? And so when you're getting down in here on a submarine, we can tweak our oxygen. So when we want to have field day, we want everybody up and cleaning and working. We actually crank the oxygen up to about 21%, maybe 22%, and everybody in the boat feels good and has energy. When we want you to sleep more, we lower the oxygen level a little bit, and you have a tendency to want to yawn and go to sleep more. That's pretty scary, isn't it? You got to trust the guys on the boat that they know what they're doing, right? But it's important to know that, because when you start losing oxygen, you start making bad decisions and you get tired. And if you lose enough oxygen, you're just going to pass out and fall over. That might be good, because you might fall below the asphyxiant level and get enough oxygen in your lungs in your next breath. It might be bad. All right, so let me show you some of this stuff that's kind of cool. So here's one. I'll just show you what these things look like when we run them. You move it over here. Oh, there's one, by the way, that we've run, just an isosurface cut. So this one's actually just showing the air handling equipment. So this is actually the air handling equipment coming in. The redder it is, the higher the velocity. You can see it's creating an eddy current down the wall and across the floor and back out the door. All right. So that's kind of important to recognize. I'm going to go ahead and let this run one more time, because I want you to burn this in your brain. And we're measuring at these two surfaces, right? So we're measuring every square. You can see the little squares we're measuring. So it's coming over here, and it's forming eddy currents across the floor and across the top right here. And shoot, I should have caught that right there. So let me get it. It doesn't work like other stuff. All right, never mind. All right, but you got it. So let's look at an acetylene release. So this is the same room. These might be at slightly different angles, but it's the same room. You see the gas coming out. The gas is buoyant. It's got a specific gravity less than 1. It's going up. It's hitting the ceiling. The air handling equipment will impact it. But remember, if you remember what that air handling equipment looked like, it had a pretty steady stream over here on this side of the room. It hit this wall. It made some eddy currents here along the wall and eddy currents across the floor, and it moved back out there. So eventually this will go out, but not until there's a lot of gas in the room. So I'm going to put a detector, if I'm trying to detect acetylene, in here somewhere, right? Probably not right beside here, because I might miss the leak, but I'm going to move it up, put it close to the ceiling in this area. Let's look at an argon leak. That's cool. This guy's heavy, right? So 10-second run. In 10 seconds, argon, and it's dissipating pretty rapidly, right? So it's not a big deal. It depends, right? Depends on what you're doing. This particular lab is a place that makes gases for other companies. They have all kinds of gases in here. The pictures of this room look like a typical facility. Here you can see the actual, so this is hydrogen running in high. And you can see that the air handling equipment's beginning to disturb the hydrogen cloud within 10 seconds very easily. So here we'll do nitrogen in high. Hydrogen being obviously a flammable gas, very extremely flammable with a very high acceleration rate or flame rate, and nitrogen being an inert gas that we breathe every day, but a potential asphyxiant in this space. And then I'm going to run, okay, so remember this one, right? Let's run this one more time. And I promise I'm going to stop talking and take questions. So you see what that looks like. It goes up, forms a cloud up here at the ceiling. Eventually it's got to get infected by the airflow and it's going to move out of the room. Let's do a low leak, a low speed leak. So this is with the heating and air conditioning equipment running. The leak's the same. The HVAC equipment's running at a different speed. So you see me ask questions sometimes like, hey, what's the speed of the air conditioning? I don't know if you noticed this, but this doesn't disperse very well. It's formed a real cloud up here. All right, so depending upon the space, depending upon where the worker's working and stuff, this could cause a problem. And so those are the kinds of things that we do to figure out whether we actually have an issue. All right, real quick. Availability. Got to figure out process failure on demand, right? So if I ask for the fire and gas system to work, will it work? All right, so you got to go through and do that mathematically. This is showing our Vertigo software doing a safety function, a SIF in this case, and the mathematics behind it. It just as easily be. And then verifying system effectiveness. We're taking the same graph basically that we used earlier and going through and saying, okay, now I have a fire and gas system and basic process control. The controller's probably going to work. So I have an 80% chance of detecting it, or 60% or whatever, depending on the area, or 90%, depending upon the area. I have my system availability of control systems, typically 90%. You can rely on that. Process PFD is, you have a 10% chance of it not working in a year. And so you go through and you do the calculation. So 80-20, 90-10. Do the math and figure out what everything is. And in the bottom, you end up over here with, I apologize, I have a little window over top of it, 7.63 times 10 to the minus fifth when we started out at 3.75 times 10 to the minus fourth. And by the way, you can do this ahead of time. You can kind of work this out and figure out what the value is and how far you want to go. All right. Oh, I'm sorry. In the end, when we're done, we tell you where gas and fire detectors go, what type they are, what settings they're at, what angles, what, all that kind of stuff. Scope, results, process descriptions, hazards, fire and gas zones, all this kind of information, including a very precise list of where to put your detectors and why. All right. Kind of cool. A little bit about our company, established in 2004. We have an office here, office in Houston, which is where most of the ISA classes are taught in Houston. And we have an office in Abu Dhabi. Apologize. We used to have an office in China, but based on current events, we do not have an office in China anymore. We are active contributors, teachers, authors. I'm actually the vice president of the local ISA section. I am on the ISA 84 committee and the 99 committee. I am a member of the ISA 84 Working Group 9 that's working on cybersecurity for process safety, and I'm also on the cybersecurity standards body. We develop, revise, and teach the ISA EC 56 course, which is performance-based fire and gas mapping. We are active members of the Purdue Process Safety Assurance Center, which has tested all of our mathematics. You might get a kick out of that, to make sure that the way we're doing this is correct. And they have found that the way we do this is the best way to do it known to man today, which is cool. We write books on the subject. You can get a book from the ISA. The handbook on the right, you got to ask me for it. And shipping's expensive, so we'll work something out. We have some patents. One of the patents is on plume modeling and the effigy software. Support can escalate all the way up to when we sell or license effigy to somebody to use it, we provide software support for free. If you get to a point where you need to know how to do something for our regularly hour rate, we will teach you how to do something, basically how to do part of the process if you need to. If you get into trouble, you can actually subcontract us to finish the project for you. And all you have to do is, because Effigy runs in our safety suite, all you have to do is go in and give us rights to your project and basically give us a purchase order based on the estimate that we give you on what we think it'll take to finish the project, and then we'll finish it for you. So there's a lot of safety built into the system. I'm going to skip that slide completely. So people always ask me, how do I get a hold of you? You guys are special because you have my email, because I sent you an email in the last 24 hours saying, hey, this event's going to happen. But if you ever forget, you can go to the Connexus.com website and you can click on the company or any contact form, as long as it's general inquiries, where it just says contact Connexus, not tech support. Tech support doesn't come to me, but contact Connexus comes directly to me. Hey, thank you very much for listening all the way through this presentation. I hope it was a benefit. If you have any questions at all, don't hesitate to contact us at www.connexus.com. And you can go to the contact form and get to me directly. Thanks. Bye-bye.